kinetic. So this 7 harmonic happened to be such that it changed sign and all the flow goes opposite to radial flow, so it becomes the deep. And we didn't invent this. It was invented in space. This maxima and minima in multiple moments on the sky of cosmic microwave background are exactly of this origin. So there is this exponential decay that's dating, and there are maxima and minima. These are Planck data. There are now better data with a couple of more bumps. So at that time, people, I said, oh, look, there are these 50 points. And maybe we did have something interesting above 7. And people say, okay, that's nothing. This point is just 0, and this point still have legendary mass. 10 years later, or 9 years later, Alice came with the data, which is shown on the right. This is the latest. So you see different centrality, first of all, this is one centrality. And in all of them, you see that there is a minimum and somehow the signal goes up. So whatever happens with 8 and 9 harmonics is interesting. I'm saying it's a play of the phase factor, and at least the minimum is experimentally confirmed. That's my signal. So we understand something about these harmonics. Again, people who calculate this hyperdynamics on event-by-event basis have very big difficulty going to say 9 harmonic because statistics is magnitude is very small. It's hard to get. Okay, now my message here is that the physics is very similar. There are little initial bumps. Each bump generates its own circle. They are not correlated between each other, so it is enough to study one of them. And it generates a spectrum. And this spectrum is interesting because each harmonic has its own dynamics and rotate in time. And by result, some of them have positive and negative phases. That's my message. Now we go to the Big Bang. And we know that KGP is not transparent to quarks and muons, but transparent to the electrons and photons. That is a big story, and I will not go into it. But just a question, if we go to the universe, do we have penetrating probes? Yes, we do. It's a gravity waves. So now, of course, gravity wave is a big thing, and the question is, what is the interaction between, what is the production of sounds, what is interaction between sounds, and whether sounds can generate gravity waves. That is what I'm going to discuss. Here I remind you this penetrating probes. So these are the original calculation of rates for photons and the electrons, and they are proportional to electromagnetic coupling, therefore it is small. So photons and the electrons are penetrating. Again, Roy Schweinberg, shown here, was saying that there is this increase factor, because if hydrodynamics lasts longer and longer, which we call putting quantum plasma in a can, hadrons cannot leave, and photons are produced, and electrons are produced all the time. So he called it photonization. No, it's not much photonization, but basically in our language, we say hadron production is the surface integral of a phase-out surface, and the electron and photon production is a volume integral. So the duration of a fireball appears as a factor in some sense. Okay, so you can of course calculate in a formal background production of gravity waves. This 1/m Planck is basically basically Newton constant, and you get something but very little. I should emphasize that if we go to initial state of cosmological phase transition, the QCD phase transition and the weak phase transition, you have temperature, which gives you microscale, and time, and the time gives you macroscale. In the case of QCD phase transition, it is some microseconds, and temperature, of course, is our critical temperature. So there are many orders of magnitude between them. This number is for electroweak, unfortunately, I forgot to change the QCD. But it's also many orders of magnitude between them. And the question is, what happened in all this? So you see in fireball, we start from elliptic flow, which has a wavelength of half of circumference of our fireball. So this is, so to say, the most infrared sound mode, which can fit in the fireball. And then we go to higher harmonics, etc. Here, I'm saying we start from microscale, go out to larger scale, and ask the question, can we have large interpretations? The thing is that there is a theory of turbulence, which is, and also there are some stationary tractor solution. It is not the ones which Paul was just speaking, but they're similar in nature. So it turns out that depending on dispersion curve of sound, there are two regimes. One regime, and that depends on next coefficient in dispersion curve. So omega is ck times k, cs, speed of sound times k, and then there is a term k cube. So depending on sign of that k cube, which is I call a, right, the dispersion curve here, it will show up later. So if this coefficient of k cube is positive, then one phonon can decay into two phonons. And that has a particular cascade, and this cascade is inverse cascade corresponding to some negative power like this. If it is the other sign, then it cannot decay, and then the cascade is done by usual scattering of phonons. What is important is that this turbulent cascade, which is inverse cascade, inverse means everything goes toward infrared, which means many small sounds glued together into larger and larger and larger. We know such phenomena, inverse cascade, in Earth atmosphere. So there are small vortices combined, and become larger, 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 and create a huge storm on the infrared cutoff scale. Infrared cutoff is the size of Earth. So we have these huge cyclones, anticyclones, of the size of 1,000 kilometers or so. So we know that if there are little sounds, the sounds can somehow by themselves get organized and generate big storm. So the question is, can there be similar phenomenon in the universe after QCD phase transition, for example, when many phonons combine together and create a very large amplitude, very long wavelength phonons. So to say big storm. Of course, there is a cutoff, and the cutoff is horizon at that time, our continent. So we wrote a paper about this acoustic cascade with 10-hour postdoc, and under condition with which I will not go, there is this cascade we can learn what is this index. The index is this S, and it tells us that at the smallest possible k, And then the question is, what happened in this case? So if you want to generate gravity, you need to calculate this correlator, which is TMU, space tensor, points, and then here, and that generate gravity waves. So this is very well known formula. People study phase transitions numerically, electroweak more than QCD, but it doesn't matter. So if you have some inhomogeneities during phase transition that create radiation. And then what was found in this calculation is that normally they were done like this. There was a phase transition, say electroweak transition. It was symmetric phase going to broken phase, everybody get the mass, and there was some inhomogeneities, and you calculated the radiation. And then once we start calculating for later time, later than when phase transition is completed, the new phase is done, and they still calculate this correlation function, and they discover that the phase transition is done, but the production of gravitons continues. Why is that? That's because phase transition is done, but long wavelength sound are not dying. They persist, and after they persist for a long time, if the two phonons collide, they produce a graviton. We discovered this diagram. So if you take TMU, and TMU is, for example, epsilon u mu u nu, two velocities, and if this is one sound with one momentum, sound with another momentum, it contributes to this diagram. In other words, two phonons going with some angle, which is like 120 degrees to each other, can generate energy and momentum on shell for gravity waves. And it's a very funny collision of two sounds which generate that gravity. Okay, and what is important prediction from this paper was this, that if this cascade go all the way to infrared, and infrared we know it is the size of the universe at the time, or horizon, which is for QCD phase transition, the size is, the time is microseconds, and the size is kilometers. So basically, the universe has a size of a little town. And that is our cutoff. Now, if you take this scale and translate it what it is today after universe expansion by many orders of magnitude, you find that microseconds become time of the order of a year. And that was one of the statements. So if we generate gravity waves at infrared at QCD phase transition, the period should be 1 year. So here is more precise time. Redshift is ratio of temperatures on scales. It is 10 to 11, roughly speaking, between now and then. So, of course, microseconds become 1 year. And it cannot be observed by ordinary atmospheric indicators. So we show it. The ordinary LIGO measures with the famous gravity observer work at about 100,000 Hertz. This is where the famous discoveries are. This is a project of interferometer in space, which is still not there. And finally, on the left-hand side, you see some curve, and this arrow, which I put here, is the inverse here. So here we expect this very long wavelength gravity waves. How people want to measure it? This is how. With the pulsars. So pulsars are very accurate clock, and the pulsars are many. There hundreds, which if you take the quickest one, if you follow the phase, this is more accurate. In principle, it is estimated that in our galaxy it should be many thousands of them. But let's stick with the ones which we have. And imagine that there is a gravity wave going into the black hole, and because it's transverse wave with transverse polarization, this length and this length oscillate in counter phase. So when this length becomes shorter, this length becomes longer. And that is because of this quadrupole nature of gravity. So what we're supposed to see, that as a function of time, for a period of the order of a year, as I said, all phases of all pulsars in this direction collectively start deviating. The phase would be oscillating with the period of the wave. And it would be correlated in this direction, in the orthogonal direction. In principle, there is some correlation function which one can easily calculate. So that was just general ideas. These ideas, of course, not ours. The idea of this cascade and infrared was ours, and what happened, and in this paper, which is last year, it's exactly a year ago, roughly, finally, one of the collaboration, which is called Nanocurve, which is measuring phases coming from pulsars and correlate them, have announced that they see the effect. This is their data. Don't look at the curves. This is some imagined form of a spectrum. Look at the points. So these points are true inaccurate. These 2 points are the signal. And as you see, it is, so 1 year, remember 1 year is 3 times 10 to the 7 seconds. So this is roughly a year. And they have a signal. I'm not claiming that theory was cascade producing, but at least the period coincide. So if there will be radiation from infrared cutoff of the our, so to say, biggest possible fireballs of kilometer size at early universe, that would be hit on a horizontal scale. What about vertical scale? Nobody knows. So that's actually everything I wanted to say here, and this is my summary. So there are sounds in the little bag. The second harmonic is elliptic. In order to understand what is the wavelength, you need to take circumference of a fireball, 2 pi r, which is about 40 Fermi, and divide by n. So elliptic is has wavelength of about 20 Fermi, believe me or not. So it's very long wavelength, and it exists for a long time. Now, higher harmonics are then with exponent of minus n squared. So it means that's why we don't see them. They go away and become very difficult to measure, so we can measure it up to about, let's say, 9 or 10 harmonic, which means we take out 40 Fermi, circumference divided by 10, it is still 4 Fermi wavelength. Okay. So it is still long wavelength thing. We understand dependence on n, depending on size, and many different things about them. And of course, there are brute force hydro from initial condition. At the initial condition, if the bumps are large, we need to improve hydrodynamics. There are some nonlinear interaction between the sounds, etc. That is speak about, or have not spoke about. The thing is, which is get very little attention, is that the phase vector, you can follow the phase in the analytical calculation, and you find that at n about 7 or 8, a minimum is predicted because this particular phase makes a whole circle, and velocity start to be against the usual gradient. Now, in the Big Bang, I mixed actually two things. One was cosmic microwave background, which is produced at late time, and this is this surface. This is result surface for photons, and we also see sounds, maximum, minimum, etc. Here. But then I spoke about completely different epoch of temperature, the confinement transition, 185 MeV, when the universe is very dense. Photons, of course, cannot propagate, but only gravity waves can. And the suggestion is that if the conditions are met, which I didn't specify, then there is inverse cascade with an index, and sounds glued together into a large storm, and this large storm can generate gravity wave on the. So it's not yet calculated in magnitude, but this is all hypothetical. But at least the infrared scale, the size of the universe at QCD transition correspond to day to 1 year time, and hours means for there was QCD transition in brackets electroweak, so electroweak phase transition give another possibility at this time. And the exciting news a year ago was that pulsar diamond correlations see these waves. By the way, actually they see, so it's half of success. They see pulsating correlation of pulsars, but anti-correlation at 90 degrees, which I spoke about, was not yet held to verify. So the fact that this is a wave of gravity, a quadrupole wave, is not yet confirmed. It is just this. So I stop here. How are you? Am I at time?
Yes, thank you, Professor Surya. So, if there are some questions, would you like to take that?
Sure.
There is any question from? You have to come here.
Yeah, I hope Vikash liked it, because he was thinking about our big